Hi, everyone. So my name is Frank, and the title of this presentation is Hijacking System Calls with Ruby. So a few words about me to start this presentation. So my name is Frank. I'm a French guy living in Walnut Creek, California. It's been a year. And I'm working for a company called Omada Health, and we are located in San Francisco. I gave a talk last year, and I was saying that my Japanese skills were embarrassing, and I think that this year they are way worse. So I don't know how I managed that, but I did. And also, I have a passion. It's embedding Ruby in things. So it started like in 2014 when I discovered that PostgreSQL had foreign data wrappers, which are a way of exposing a table in Postgres, but the data that is being used by that table is actually produced by a Ruby script. So as an example, that's what I presented last year, and I've built a product called Holycorn, which is a way of accessing, as I was saying, tables that are backed by Ruby. So you basically create a class. You can iterate over that class using an enumerator. You go into Postgres. You create a foreign table called Holy Table in that case, and you give it the wrapper path, which is the source code. And then you go into Postgres. You select something. And oh, magic, that's produced by Ruby code. So it was kind of nice. And it became kind of like a passion. So in 2015, I kind of did the same thing for SQLite. Even if it's still a prototype, it kind of worked. And this year, I've been trying to do the same thing with Redis. So Redis has this nice thing called the loadable module system. And that's also a way of extending Redis with custom code. The interface is only C, so I wanted to build something with Ruby. So basically, it's providing a way of creating new commands and exposing them in Redis. So there are nice examples of that on the web. You can even plug in a full text search engine into Redis and use it. Next year, there's something I wanted to also experiment about mruby, is trying to distribute computation across the network of mruby processes. And I guess I'm going to blog about that in a few months. So back to this presentation. So what are we going to learn? We're going to try to discover what's a system call again, for those of you who don't really remember about that. Why hijacking system calls is kind of nice. How to integrate with mruby, and a side note about performance. So if you take a look at the documentation about system call, so a system call is a request in a Unix-like operating system made by a software interrupt by an active process for a service performed by the kernel. So when you read that and you don't know anything about system call, you're kind of bummed out. So long story short, it's the interface between your programs and the OS. I mean, it's not really anywhere about your program. It's about the low-level libraries that your program is going to use and the actual operating system. So if you have a Ruby script that does file open of a file and writing in that file the string hello bang, it's actually glibc or whatever library that is wrapping those system calls, and they're going to talk directly to your operating system. So if we take a very, very simple example of that, same thing, we open up a file and we do a getS so that the process is hanging so that we can try to debug. We're going to try to discover what are the system calls and what they do. So in that case, it's about open. So you hit Control-Z, you get a PID out of this. Then you're going to use LSOF. So the man of LSOF is list open files. So it's going to list every open files of that PID. And you're going to have a long list of all those open files. I mean long, it's not that long actually. But at the end, you can see that we've used the open system call, and this file, my file, has been opened. And on the fourth column, we have the file descriptor, and the file descriptor is in this case, 7. The little u is to say that it's read-write. So if we go back to that file, once again, it's a process. You have the OS. You use a system call to communicate to the OS that you want to open a file. The OS is going to respond with something. In this case, it's a file descriptor. You use that same file descriptor with another system call, which is write in that case. And the OS is going to say, yep, 6 bytes have been written. So why would we hijack system calls? So there's something kind of nice, and and it's the fault injection. So basically, it's like a chaos monkey. So if you don't know about chaos monkey, it's like a way that Netflix provided. If you have like a group of processes that are working together, it's like a tool that allows you to like kill any one of those processes to see how the whole system is going to react. And it's pretty nice. So you can do the same thing when you hijack system calls. It's like a way of simulating a lot of things, like from memory allocation issues to slow throttled I/O, network issues like lost packets, net splits, memory corruption, like anything. So you can actually like try to implement this chaos monkey at the system level so that you could see like your programs that like maybe require to open up a file or write something to the file system, and that doesn't work. So you want to see how your program is reacting to that. I think one good parallel is the mutant gem in Ruby that is like doing crazy things with your code, like trying to like, you can like maximize the coverage of your test, and that's pretty much the same thing here. And there are some libraries that exist on the market that do and they do fault injection, but they were not like super extensible and not providing like a good API. So I kind of like rebuilt everything from scratch when I had to. There's something kind of nice also. It's doing the real-time or like interactive monitoring of a Ruby app. So to see every system calls that are being made by the Ruby process. And you can like put that maybe into a statsd process or like into any kind of database for later analysis. That's also something I've been building. Last but not least, I feel we can do better than FakeFS and timecop when it comes to providing like a layer of security. And what's wrong with like monkey patching Ruby, like just like as timecop is doing? I think it's kind of brittle, and it doesn't prevent like custom Ruby code from accessing like the real time. And also when you shell out, like the process you're going to shell out to are not going to use this monkey patch. So basically, you're going to have maybe, let's say, your Ruby process is shelling out to a PDF generator. This PDF generator is not going to like respect the time you've set in your Ruby code, and you're going to be bummed out. Securing Ruby apps has also been something I've been investigating on, and it's pretty hard. So why is it hard? There are many things where it's hard. Many reasons why. The first one maybe like when it comes to gems, when you do gem install, it's basically like curling URL and putting everything into bash and like wait for something to happen. Specifically insecure when you do sudo in the mix. It's not really about whatever is running into that in that Ruby gem, but it's also about like just installing something is going to run like the reg file and it's going to like deserialize the YAML, and that is insecure by default. And also there are some defaults like the kind of did you mean type of feature there is in Ruby gems. So if you do gem in or gem I, it's actually going to do like it's going to call install because it recognizes that I can only mean install. And there's a way that I kind of like discovered by mistake last year, and there's a way to replace the default like gem install command to do whatever by just like extending and deallocating the default install command. I reported it, but it was not really. It was a feature more than a bug for the maintainers. And I was kind of like, meh. Auditing code also is kind of hard, especially when the code is self-modifiable. There was one very good talk by Ben Lee Smith at Rulu 2013 in France, a conference I was organizing. And he was talking about how he was exploiting the actual mechanism of like gem install by just hijacking everything inside of it and like getting everything from your computer, like your SSH keys, Bitcoin wallet, whatever. And some companies are subject to regulations like HIPAA compliance or PCI compliance, like in the US. And auditing like those gems are super hard. So yeah. And I was wondering, so when you do a gem install, it's actually, so installing the gem, there's something that is called gem fetch. So you're going to download the gem. Is any one of you here, raise your hand, are you using gem fetch sometimes? Cool, one. Thank you, Eric. So this one is the only that is secure. You're going to download the gem, and you can just like scrutinize whatever is happening inside of it. So some of my colleagues have been telling me, but why don't you use Alexi, Docker, Linux capabilities, Solaris zones, like anything, to provide this layer of security? But it's really not the same thing. It has nothing to do with that. So how do we replace system calls? And the answer is actually in LD, the dynamic linker. There is one environment variable on each system. The first one, LD preload on Linux, and the other one, DYLD library path on OS X, on macOS. And if you set them to something, like to a shared library, you can hijack the system calls. So it's pretty much like a renowned way of doing that. So back in C now, how would you do that? So you would use DLSym, and DLSym is a system call to get a method address, a function address, based on the handle and a symbol. So if you had to do it, so the first thing, you have to respect the read interface, and the read interface takes 3 arguments. The first one is a file descriptor, the second one is a void star, and the third one is the number of bytes you want to read. Then you have to define a new variable, and because this variable is going to hold the original address of the system call wrapper that is read. And then based on that, you can, like based on some variables, you can either call the default implementation of read or hijack read to do something else. So you could like modify some things and hijack and execute the original method, or you can like decide to do something else entirely, like raise an error. What is cool about library preloading is that it does not require recompilation of your programs. So you can just inject any shared library you want. Things are going to work. It is something that is pretty much used by, I would say, everybody. But in any case, you can replace like malloc with jmalloc or with whatever library you want. But that's something that people do. And also, it's kind of bringing a dynamic way of doing things when none has been built in. So wrapping the system calls, how do you do that with mruby? And so first of all, why mruby? So first of all, it's because it's Ruby, and I'm kind of proficient with Ruby, so why going somewhere else? The second one is it's kind of easy to build a higher level interface and bringing an external DSL and wiring this C implementation of Ruby in any type of like C program. So how would you do it? So let's take an example with those 2 system calls, truncate and ftruncate. Truncate and ftruncate truncate a file being as a path or as a file descriptor to a specific length. So it's kind of easy to map that to a Ruby interface that do exactly the same thing. Something that I've built also in that program is that super is actually calling the original implementation of truncate, of ftruncate in that case. So you can do your logic, raise an exception, or do something else, like remove, I don't know, like inject something in the file descriptor, modify the size, and then you can call super, and the original system call is going to be called. So if you remember that slide about the library preloading and DLSym, it's as easy as injecting an mruby fun call into the mix and trying to run the Ruby script that is associated with that system call. So embedding mruby is kind of nice, and I think that's why I think mruby is my preferred implementation of Ruby, because it produces low-level artifacts, and you can link against them. It's producing static libraries. You can even like try to modify it a bit to generate shared libraries. So how would you do it? The tool I've been using so far is mruby CLI. And mruby CLI is kind of new, so like 2 years ago I was not obviously using it, but it's a way of like establishing the base project tree. It's going to create the files that are required to build an mruby CLI. It's a Docker-based solution. So for those of you who attended Eric's talk yesterday, he presented everything like in more depth than I'm going to present today. but it's pretty much like using like wrapping around Docker right now. And also, it's going to cross-compile to a variety of environments. So once you run this Docker run, you're going to have a lot of, so those are the default targets. But on OS 10, for instance, you can generate the portable executable for Microsoft Windows. And yeah, that's going to work automatically. You don't have to do tons of things. At the end, it's also going to produce like this archive, this libmruby archive that you can link against anything using GCC, and you basically just bundle up with mruby. It's highly modular, so basically the standard library is modular. So it means that even if you want puts in mruby, you're going to have to install and link against the mruby print gem. So everything is so modular that you can like fine-tune whatever library you want to use in your programs, which is kind of cool because if you're running on Arduino on an old Raspberry Pi or like a very, very constrained device, this modularity is like crucial to your work. Something else that I've been waiting for in the actual C-Ruby implementation, but is like by default in mruby, is a multi-VM in a single process. So if you link against C-Ruby right now, it's going to be hard for you to have two different VMs at the same time, and probably impossible right now. I'm not sure about this. But with mruby, it's by default. So you can have like 20 VMs, and that's still going to work in a single process. So a side note about performance, and that's where it got ugly at some point when I was working on that. So if you want to reproduce whatever work I've done, so not only there's going to be a GitHub repo containing everything, but just so that you can reproduce and get some, like, make some comparison. That's a program I've been using. So basically generating 100 strings with foobar and then an increment, and touching those files, like creating those files and removing those files from the file system. That's the program. The hardware, it's a Core i5 2.7 gigahertz and 8 gigs of memory, if that matters. So the first naive implementation of this system called hijacking type of program was trying to hijack unlink, because RM is actually using the unlink system call. So basically, at the top of this function, we create a new VM with mruby open. We open up a file, the policy.rb. We load the file, and then we call some methods inside of that file. I've made a benchmark program. So bench bare means there is no mruby involved in the mix, and bench naive is this naive implementation benchmark. So we went from 45 milliseconds to like more than a second. So it was really, really freaking slow. So like 20 times slower than the bare process. So it was not good at all. The second implementation was what I was calling the optimized implementation. So it was a way to have only one VM per subject under test. So basically only one VM every time you're going to call unlink, for instance. There's a nice way of running something when a shared library is loaded. It is the attribute constructor here. So the code here is going to be run every time you load that into memory. So it was also a way to get some arguments from the environment, like the isolate optimized thing. And based on that, at the top of the unlink function, it was also a way to like make a switch. If it's a single persistent VM, just get the VM that already exists or create it. But if there's no optimization, so it's like the first implementation, the naive implementation, create a new one every time. As a result, so that was a previous results. With the optimized version of it, we went down to 84 milliseconds. So it's like twice slower than the bare process, but it was still fine because we were instrumenting the thing. So it was cool. So as future work, there's something I wanted to do to try to understand mruby better, and specifically the performance of mruby was adding dtrace probes to mruby to understand everything that was happening. I wanted to know if it was a parsing or the actual implementation of mruby, and where in mruby that was my things were slow. And also, if you want to address the startup time, maybe mRBC, which is a way of converting Ruby script to bytecode, could help. So, as a conclusion, replacing system call was kind of fun. It was the first time I was dealing with that type of stuff, and I was learning about LD preload. But it was kind of easy actually to do it. There's ways to escape the protection I was describing, because it's only when you export this LD preload, only the current session is going to use that shared library. So basically, maybe running as a kernel extension could be something that can be done. And I kind of love the idea of running Ruby at the kernel level too. As I was saying, mruby is still my preferred Ruby, not only because it's lightweight, but also because it's flexible for the reasons I've mentioned. So having multiple VMs in a single process is kind of awesome. And also being able to choose whatever functionality you can put inside your standard library is awesome. Arigatou gozaimasu. It is the end of my presentation.